is so everything is a revision of what you've done in KC in your AS, and then you're going to build on top of that. So I'm going to quickly start off with the Lee Chatelier principle, not spend a lot of time on that. So for example, uh, Lee Chatelier principle and equilibrium. So we'll just quickly. You've studied this in O levels as well in AS. So what's a dynamic equilibrium? What's the definition of that? When we say that something is has equilibrium, has reached equilibrium, that means that the rate of forward reaction equals the rate of yes. Sakib, it's a new topic. Okay. So dynamic equilibrium is rate of forward reaction equals the rate of it equals the rate of backward reaction. So equals the rate of backward reaction, and that can only happen in a reaction that is reversible. Not all reactions are reversible, and it has to be a closed system. I mean, that's not a necessary requirement for the definition, but it has to be a closed systems. Like things, they shouldn't escape the container. So that's one thing. That's what an equilibrium is, and you're already aware of what an equilibrium is. I'm sure you all of you know what an equilibrium is. So, for example, uh, you've got your water example. Like there's a water bottle and there's water liquid, and it doesn't seem to evaporate. Why? Because it is constantly evaporating. It's turning into H2O gas, but at the same time, the water vapors are changing back into liquid water as well. So there's a reversible reaction that's happening. H2O liquid changes into H2O gas, and rate of forward reaction and the rate of backward reaction is equal. Whenever something is at equilibrium, one thing that's not going to happen is that the concentration becomes constant. It doesn't change. All of them can have different concentration. Like the amount of water vapors could be a lot, or the amount of water vapors could be very less. Okay, so the quantity of products and reactants, their quantity can change, their concentrations can vary. But the thing is, if the reaction is at equilibrium, the concentration is going to be constant. It's not going to change, because every second, if there's a certain amount of water vapors that's getting formed, then at the same time, that same amount of water vapors is turning back into water liquid as well. So the quantity remains exactly the same. So it appears that everything is not changing, whereas in fact the reaction is going on. The forward and backward reaction is happening. So there's a Le Chatelier principle that goes along with this, which is that if you do anything to the equilibrium, it's going to try and do the opposite. So the Le Chatelier principle simply is that the equilibrium opposes any change that's introduced to the system. So it's going to do the opposite. So number one, if you increase temperature, what's going to happen? Which reaction would be favored? Anyone? What's the answer to that?
Endothermic if it's on the right side.
It's going to be
Yeah.
I'd say it's going to be endothermic reaction that's going to be favored, not right and left, because every reaction the endothermic. I mean, in this case, it's going to go to the right side. So endothermic reaction is going to be favored, and every time you have to check whether the forward is the endothermic reaction or the backward is the endothermic reaction, and vice versa. If you decrease temperature, it's going to be the exact opposite. That's going to happen. So the exothermic reaction is going to be favored. So what happens if you increase pressure?
Pressure favors the less number of moles, so no effect in this equation.
The less gas mole side, it's going to have an effect. Less gas mole side would be favored. So remember, pressure only, you have to count the gas moles. So there's 1 mole of gas over here, and there is no moles of gas over here. So which side is the less gas mole side? It's going to be, uh, that is going to be your this side. It's going to go to the backward side. Backward reaction would be favored. I mean, like if you compress this container, there would be less room for water vapors to form. So if you increase the pressure, you're compressing it. So there's not enough room for water vapors to form. So there would be less water vapors formed, and they would turn into liquid water. Is that clear?
Yes, sir.
Yeah.
Okay, so if I increase pressure, you're decreasing volume, so less gas would be formed, and always focus on the less gas mole side. And then you've got the opposite. If you decrease pressure, that automatically means what you're trying to do is you're expanding, you're increasing the volume. If you increase the volume, automatically there's going to be more room for water vapors to form. So more gas mole side is going to be favored. There's going to be more gas that's going to be produced. And then you have so I said, so if something doesn't really have gases in it, the pressure is not going to have any effect on that. If a reaction doesn't have gases in it, no effect. Similarly, if gas moles are equal on both sides, again, then there's not going to be any effect on of pressure on the equilibrium position. And the last one is that if you increase or decrease concentration, equilibrium tries to do the opposite. And remember, it's focused on the word concentration. It has to be concentration. If you increase concentration or decrease concentration, so the equilibrium favors that reaction that does the opposite. So if you increase, it's going to try and decrease it. If you decrease, it's going to try and increase it. So for example, over here in this container, if I remove all the water vapors all of a sudden, what's going to happen? If I go in and remove all the water vapors, equilibrium is going to try and do the opposite, because evaporation is still going on. The condensation reaction would immediately stop because there is nothing to condense, because I've removed all the water vapors. So this reaction is still going on. So more water vapors would appear because there would be evaporation happening. So I tried to remove them. What did the equilibrium do? It just made more of them. So it did exactly the opposite. And if I try to increase them, like if I open the container and I add a lot of water vapors into the container, into this mixture, then all of a sudden there's going to be more condensation happening because you have more water vapors now. So if I try to increase water vapors, it would automatically, I mean, it's obviously, it's common sense that condensation would speed up and the amount of water vapors would automatically start decreasing. So it's going to try and do the opposite. I try to increase it, it's going to try and decrease it. I try to decrease it, it's going to try and increase it. So is that clear? All of these points.
Yeah.
Yes, sir.
I said now, so that is all about Lee-Chatelier principle. Okay, so we're not going to do any practice for this at the moment. What I'm going to there's one thing that I want to focus on is that equilibrium is a comment on equilibrium is not a comment on rate. So a comment on equilibrium is not a comment on rate of reaction. They are completely two different things. Rate is something else. Equilibrium over here it means something totally different. For example, if I tell you that there's N2 and there is H2 and they're reacting together and it's 2 and it's 3, and I ask you what's going to happen, delta H is negative in this case. delta H is always given, the enthalpy change is always given for the, it's always given for the forward reaction. So in this case, it's exothermic. That means the forward reaction is the one that is exothermic. It has a negative sign. The backward is going to be exactly the opposite. It's going to be endothermic. I said now, if I tell you I'm decreasing temperature, where would the equilibrium shift, and which reaction would be favored?
Forward and to the
Forward.
right.
The forward, the exothermic reaction, right? So the exo, which in this case is your forward reaction, that's going to be favored, right? So that's a comment on equilibrium. What that means is that's not a comment on rate. It means that the forward reaction is in relative terms faster compared to the backward reaction. I mean, when we talk about equilibrium, we're basically comparing the speeds of the forward and backward, and we say that the forward is slightly faster compared to the backward. So maybe both reactions are speeding up, right? But one of them is faster compared to the other one. Or maybe both reactions are slowing down, but one of them is still faster compared to the other one. So remember, try to understand this, that a comment on equilibrium is not a comment on rate. It doesn't tell you what's happening to the speed of the reaction. It just tells you that when we say that the forward reaction is favored, it just means that the forward reaction is faster compared to the backward reaction. It does it, so it's a comparison. It's not an absolute comment on what's happening to the speed of the reaction. So if I ask you what happens to the rate of forward reaction, what would be the answer to this? I'm decreasing temperature. What should happen to the rate of forward reaction?
Increases.
Why does it increase? You're remember, now I'm specifically
Oh, okay.
I'm not asking about equilibrium now. I'm asking about the rate of reaction. What happens when you decrease temperature?
The reaction slows down. Yeah.
Any reaction slows down, whether it's the forward or the backward reaction. uh, Molecules lose kinetic energy, they travel slower, so the reaction is going to be, they're going to lose speed. So if I ask you what happens to the rate of forward reaction, it slows down. So that's a comment on rate now, and that means both reactions would slow down. Like if they're asking about the speed of the reaction, whenever you decrease temperature, you should know that whenever you decrease temperature, the rate of forward reaction would slow down, and the rate of the backward reaction would also slow down. Both reactions, all reactions in the world, they're going to slow down if you decrease temperature. But when we talk about equilibrium and we say that the forward reaction is favored, that means that even though both of them are slowing down, but one of them is still faster compared to the other one. Is that clear?
Yeah.
Okay, is this clear to everyone?
Yes, sir.
Yes, sir.
So just make sure that you know that a comment on equilibrium is not a comment on rate. It's just a relative comment on the speed of the reaction. And the same goes for pressure, and the same goes for uh, concentration as well. So for example, I do another example. I've got 2SO2, and the two are reacting together to form O2 and 2SO3, and they're all gases. Now tell me, I'm decreasing pressure. Where would the equilibrium shift?
To the right. Wait, sorry, to the left.
Okay, when you decrease pressure, more gas must be produced. More gas is on the left side. Okay, so the equilibrium is going to shift to the left. So backward reaction is favored. That's why I'm using the word favored. I'm not saying that it speeds up. I'm saying that the backward reaction is going to be favored. What that means is that the backward is going to be faster compared to the forward reaction. And then I ask you what happens to the rate of the reaction, right? Let's say rate of the backward reaction. What would happen to it? Would it speed up or would it slow down?
It will slow down, yeah.
Okay, so it's going to slow down because you're decreasing pressure. Whenever you decrease pressure, the particles are further apart, and they're not going to hit each other that often. So when the rate of backward reaction, it slows down. Whenever you decrease pressure, all reactions slow down. Whether it's the forward or the backward reaction, all of them would slow down. But if the backward reaction is being favored, that just means that the backward is still, even though all of them are slowing down, but the backward is still faster compared to the forward reaction. Okay? Is this clear?
Yes, sir.
Yes, sir.
I said now, just one second, let me draw. I said now, the next part is we're going to talk about. We're done with the Lee-Chatelier principle. Okay? You should know what increased temperature, higher temperature, lower temperature. What's that all about? Uh, the next thing we're going to talk about is the equilibrium constant Kc and Kp. Okay? You do get questions on Kc and Kp, and so what's Kc? When something is at equilibrium, I just told you that the concentration stops changing. Like it's not, I mean, the reactants are going to have different concentration and the product is going to have a different concentration. I mean, they can be the same, but they all can have different concentrations, but the concentrations would not change. Uh, so what is Kc? Kc is that the products and the reactants at equilibrium are going to have a certain ratio. Like if you look at the water container, there's a certain amount of water vapors that are formed, and there's a certain amount of water liquid that's present, and that ratio would be maintained. Like it's not going to change, it's going to be a constant, because like it would change if you change conditions, but it's going to remain a constant. uh, like if I decrease the water vapors, right, like if I get rid of the water vapors, there's going to be more evaporation that would happen and more water vapors would be formed back again. So the ratio of the water vapors and the ratio of the water liquid, that kind of remains constant even if you alter the conditions. There's only one thing that actually changes that ratio. uh, like if I alter it, it's going to automatically adjust to sort of balance that out. Is this point clear?
Yeah.
Right, so the Lee-Chatelier principle would work and would try to maintain that ratio. There's going to be a certain amount of water vapors and there's going to be a certain amount of liquid water, and that ratio is going to be maintained. It only changes with one thing, and what is that one thing?
Temperature, I remember, I think.
Temperature. Because if you increase temperature, then all of a sudden there's going to be more and more evaporation happening, and that ratio would now change, because at a higher temperature there's obviously going to be more water vapors. Is that clear?
Yeah.
So temperature is the only one that changes the ratio. So it's the ratio. What's Kc? Kc is the ratio of the concentration of the products. Divide that by the ratio of the concentration of the reactants. That's what Kc is. Products over reactants. And um, changes in concentration or pressure is not going to have any effect. The reaction would automatically adjust to maintain that ratio. It does not affect that particular ratio. Uh, and the equilibrium automatically adjusts. It moves forward and backward accordingly to specifically, I mean, it doesn't know it's doing that, obviously, but that ratio is maintained. It automatically adjusts to maintain that ratio. So that ratio is always maintained, only changes with temperature. You change temperature, the ratio is going to be completely different now. Okay, so that's important. You're frequently asked about this. Now, so that's what Kc is. First thing, the expressions for Kc. How do you write an expression for Kc? So you've already done this, H2 plus I2 in equilibrium with 2HI, and it's going to be Kc is going to be, so Kc is going to be product concentration. So your products are HI, and remember it's concentration. It's not moles. Okay, uh, remember that this is concentration. Highlight that you don't you don't place moles over here. You use the concentrations. The square brackets are concentrations. As I said, it's HI concentration. That's your product divided by the concentration of H2 and the concentration of I2. Now, if you have done your AS, what's wrong with this expression?
Number of moles.
Okay, so the number of moles become the exponent. The coefficient,
ये हम रिवीजन करें
हाँ क्योंकि इसके बाद ही हमने वो करना है ना A2 KC मैंने equilibrium A2 equilibrium is built on top of KC and KP, right? So coefficient becomes coefficient in equation becomes the exponent or the power. So it's going to be HI squared. That's about it. So you should know how to write the expressions for Kc. And in A2, we're going to study different versions of Kc, different applications of Kc. So there would be lots and lots of equilibrium constants. I mean, Kc is the most general form. You can call anything Kc, and then there would be just some way that it's exactly the way that enthalpy changes. You have enthalpy change of a reaction, and then you have very particular enthalpy changes, like enthalpy of formation that applies to a certain type of reaction, enthalpy of neutralization. So the same goes with Kc. We're going to study different types of Kcs in A2. Now, let's do another one. What's the expression for Kc? And you have to find the units as well, like N2 plus H2 and 2NH3. So what's the expression for Kc in this case? It's going to be NH3, that's the product. And remember, everything is either multiplied or divided. So it's going to be NH3 concentration squared divided by N2 concentration, and H2 concentration is going to be cubed. That's your expression for Kc. And the coefficient has become the power. How do you find units? The units are going to be found that you've got you've got your mole per dm cube squared, mole per dm cube into mole per dm cube cubed. So you can take mole per dm cube as x squared divided by x into x cubed, and this comes out to be x to the power minus 2. What was x? X was mole per dm cube, so it's going to be mole per dm cube, and power is minus 2, which would give you mole minus 2 and dm6. So every time Kc has a different unit. Is that clear?
Yeah.
Yes, sir.
I said then you have two types of questions on Kc. The first type is that you'll be given a reaction and equation. So for example, question number 1, question type 1. So for example, you're given that you'll be given initial moles in a reaction. So there's a reaction going on and you've got your initial moles. For example, you've got 0.5 moles of H2 and you've got 0.6 moles of I2 and there's 0.1 moles of HI. Now at equilibrium, you found out that I mean, that those are the moles that are initially added into the container. Okay, so you've put all these moles into the container and they've been added. Second. As anyway, so they're added and mixed up in the container, and a reaction starts. Maybe there might be a lot of forward reaction happening. Maybe there's a lot of backward reaction happening. So forward and backward reaction that it starts, and eventually the equilibrium would settle somewhere. There would come a point when the rate of forward reaction becomes equal to the rate of backward reaction, but we don't know at what time that would happen. So we'll wait for a couple of days and we'll see if equilibrium has been reached. Once it happens, once equilibrium is reached, we open the container and we find out that things are now different. The container looks kind of different. For example, you've got 0.3 moles of HI at equilibrium. Now, at the beginning, you just added 0.1, but now at equilibrium, you're finding out that there's 0.3. What does that tell you? It tells you that you put in zero point 0.1 moles, but after several days, there's 0.3. That means there's an extra 0.2 moles coming from somewhere. And where are those extra 0.1 moles coming from? That means 0.1 moles, sorry, 0.2 moles, they got produced. And they probably got produced because there was a reaction that was happening. So there's an extra 0.2 moles coming from somewhere. Is this clear?
Yes,
Yeah.
sir.
So if 0.2 moles are getting produced, that means because you added 0.1 and now you have 0.3, so 0.2 came from somewhere. There was an extra 0.2, so 0.2 moles got produced. And according to the ratio, if you want to produce 2 moles of HI, there should be 1 H2 reacting with 1 I2. So if you want to produce 0.2 moles, there should be 0.1 moles of H2 that would react, and there's going to be 0.1 moles of I2 that would react as well, according to the ratio. React means they would be gone. So there's 0.1 that's missing, and there's 0.1 of this also missing. So out of the 0.5 you started off with, 0.1 are gone. So that means you're left with 0.4 moles. And out of the 0.6 moles of I2 that you started off with, that you added in the container, 0.1 are gone. So you're left with 0.5 moles. Is this clear?
Yes, sir.
Okay, so you now found your equilibrium moles. You have your equilibrium moles. And the last part would be easy, that you have to find Kc. And to find Kc, what you're going to do is it's going to be the concentration of HI that's going to be squared and divided by the concentration of H2 and concentration of I2. So it's going to be 0.3 squared divided by 0.4 multiplied by 0.5. Right? Is this clear?
Yes, sir.
Yeah.
As I did I make any mistake with this expression by using these values?
Like we had to convert them into concentration.
Yeah, exactly. I mean, you don't use moles, you use concentration. And what is concentration? It's concentration is moles over volume. So you need the volume of the container. So as in now, in one case, you don't need volume of the container. So remember this, you always have to do this step. Always just make sure always do this step. Don't put in moles in your expression. It's going to be, you have to calculate concentration. Those values are going to be put into your expression. But only one time you can actually go with moles, and that is when the Kc expression doesn't have any units. Like if I take volume as V, so it's going to be 0.3 divided by V. That's going to be squared, and divided by 0.4 divided by V multiplied by 0.5 divided by the volume, right? Acha, so if the number of terms in the numerator and denominator are the same, you don't have to divide by volume because the volume term would automatically get cancelled out. Like there are two terms of v on top, that's v squared, and there are two v's at the bottom, that's also v squared. So it's basically going to get cancelled out. So the v would cancel out. So only once, if the number of terms in the numerator and the denominator are the same, which means that the Kc expression has no units, then you don't have to divide by volume because it's going to get cancelled out anyways. Is that clear? Otherwise, always make it a habit that you divide by volume. TK, is this clear?
Yes.
The
Yeah.
volume will be given in the question, right? Or
Man, it's like in this question, even if they didn't give you volume, you can you can use v and it's going to get cancelled out. But for example, the N2 question over here, the v is not going to get cancelled out. Like there would be moles of NST divided by v, that's going to be v squared, and at the bottom there's going to be v to the power 4, so it's not going to get cancelled out. So it has to be given in the question, otherwise you won't be able to solve it. And another thing about concentration, where did I put this one? Another thing about concentration is, remember for solids, if there's a solid in the expression, its concentration is going to be taken as 1, because the term concentration doesn't really apply to a solid. And anything that's in excess, for example, water in aqueous state, its concentration, water in aqueous solutions, like if it's an aqueous solution and the equation has water in it, like water is taking part in the reaction, the concentration of water is going to be taken as 1, because it's not going to change a lot. Like there's too much water, right? If you have a container and there's a, let's say there's a reaction of water going on, like water is reacting with an ester, like there's a bunch of alcohol molecules, and there's a bunch of carboxylic acid molecules, and they're reacting together to form, they're at equilibrium, they're reacting together to form ester and water molecules. Now if everything is aqueous, then there would be too many water molecules I mean, the whole container would be full of water, right? So water would be in large excess. I mean, not in excess, but large excess. Like anything that's in large excess. So the concentration of water would be a constant. Like if a couple of molecules of water are produced, like let's say if there's one water molecule that's produced in the reaction, the concentration is hardly affected. It doesn't really change much. Uh, if uh, if a few molecules get consumed, like one molecule of water goes, one molecule of water reacts, the concentration of water is still it remains exactly the same. But the concentration of these red particles, these other particles, that would change drastically. Like if two molecules of these red molecules they get produced, now all of a sudden the concentration is double. It has increased by 100%. So remember, concentrations of substances that are present in large excess, their concentration it's kind of constant, and you take it as 1. Is that clear?
सर लेकिन वन क्यों है?
Nee, acha, Adam, it's 1 because so that you don't have to write it in the expression. Like for example, I've got H2, right? Okay, like, what's happening? Just a second. Acha, so for example, I've got H2, and let's say that it's in large excess, right? Its concentration is a constant. So why do you need a constant thing over here? I mean, it's a constant, right? Just combine it with this constant, put the two constants together, get it out of the equation. So if you put a 1 over there, then it's out of the equation. I mean, writing 1 means you're not writing anything. Is that clear?
Yes sir.
So it's taken as a 1, so you don't have to write it in the expression. Why put in extra?
Then, I mean, why are solids taken as one?
As the solids are taken as 1 is what is concentration? Concentration is by definition, it is a description of how close the particles are. Like if you have a solution, right? So this is a very dilute solution. A dilute solution means that the particles are really far apart, right? And this one, now the solution is very concentrated. That means the particles are kind of really close together, right? So that is what concentration is. Concentration is not moles. It's not the quantity of particles. It's not the volume of the particles, like how much volume the solution is occupying. It is a measure of the closeness of the particles. Ibrahim, is this clear?
Yes,
Right.
sir.
So, so what about solids? Does their closeness ever change? Like if you have a solid, the particles are all always tightly packed. So the spacing never changes actually. So the concentration never changes for a solid. Is that clear?
Yes.
And the word concentration can only be applied to either a solution, like something that's present in solution. They could be very close together, they could be very far apart, or they could be, it applies to gases. Like in gases, it's the same thing, except that the gas particles are now kind of far apart. Or they can be, I mean, you can change the spacing by increasing pressure. That means the concentration would decrease. You can get rid of some of the particles and the concentration would become lesser. So concentration is all about spacing, how close together or how far apart the particles are. So that is what conceptually concentration is. That is the idea what the term concentration gives. So remember this: solids and anything that's in as a solids and anything that's in aqueous state. The solids and anything that's in large excess, its concentration is going to be taken as a constant. So that's your case. So we can do another couple of questions. I'll give you those questions. Try and okay, I'll just write the question here. So I've got A plus and 3B. I've run out of equations to think of. So this is just a random equation. So there's A and B reacting together to form C, right? I have my initial moles that were added into the container. So that's 0.5. This was 0.9, and I added 1.5 moles of C. And at equilibrium, and it's a 1 dm cube container, right? So if you want to find the concentration at the end. ठीक है साके. अच्छा, so I've your so equilibrium. What's happening at equilibrium? At equilibrium, I figured out that I've got 1.1 moles of C left, right? So I started off. So what are my equilibrium moles of the other substances? So I started off with 1.5. Now I have 1.1. That indicates that 0.4 are gone, right? 0.4 moles are missing. So what happened to them? They reacted. That means they reacted and they produced these A and B. So they took part in the reaction and they're gone. So what's the ratio? If two are going to react, then over here, three of them are going to be produced, right? So if, according to this ratio, if 0.4 react, how many would be produced over here? What's 2 ratio 3?
0.6.
Okay, so you get 0.6. They're the ones that are going to be produced on this side. And this would be what, 0.2 getting produced, right?
Yeah.
So that means you had 0.9, but now there's an extra 0.6 that are getting produced. 0.6. And you had 0.5, and now you have an extra 0.2 getting produced. So 0.9 plus 0.6, that's going to give you 1.5, I think. This would be 0.7. And if it's a 1 dm cube container, so this would be moles per dm cube, moles, and it's a 1 dm cube container, 1 dm cube container. Is that clear?
Yes, sir.
So
Yes, sir.
let's continue. I'm going to send you a worksheet on KC only. Okay, doing this right now. Try and go through those questions. Okay, clear है?
जी, sir.
Yes, sir.
And I'm going to send you the videos on those. Okay, so you can go through them. चलिए, okay then everyone. Take care.
Okay, sir.
Thank you.
Love it.
Hafiz.
Thank you.